And today we're going to be going over the 2024 AP Physics 1 FRQ, and this is the first question. So here's the situation. We have this kind of ramp thingy and it goes back up, right? We have a block that's going down. It starts at a height of 6r, and there are two circular loops that we need to keep in mind. And they give us this value r, and we're going to use that to find the velocity of this block pretty much. So when you look at this question first, the basic idea that you need to think of is conservation of energy. Because according to the question, no energy is lost since there's no friction. So we can assume that energy is conserved, and we can use the gravitational potential energy from this block, and we can apply it to find the kinetic energy at various places. So let's see the first question. So of course, it's like diagram A shows an energy bar chart that represents the gravitational potential energy of the block or its system and the kinetic energy of the block at point A. When the block is released from rest at the height 6r. So the first thing it asks us to do is draw a shaded region in diagram B that represents the gravitational potential energy and the kinetic energy of the Earth's block system when the block is located at point B, height 2r above the horizontal. So point B, that's going to be right over here. So this block's going to go down and it's going to go to this loop, and when it's at this point, what's its gravitational and what's its kinetic energy. Okay, so the concept here is that the mechanical energy is going to stay the same since there's not any non-conservative forces. So the mechanical energy in this case is going to be mgh, or in this case, right, it starts over here, so 6mrg. So we just need to make sure that gravitational and kinetic equals to 6 mrg when we're doing our calculations. So let's get right into it, right? At point B, the block's going to be 2r above the horizontal, because see, r is the radius, and once you find the diameter, you're going to see how high above it is. So it's 2r at that point. So the gravitational potential energy at that point would be 2r mg, right? Because it's mgh, and h in this case is 2r. So what percentage is that of the original, right? Think about it. It's a third, right? It's a third. So in here we see there's 1, 2, 3, 4, 5, 6. It's 6 units high. So since it's a third in this case, we could do 2 units. There we go. And as mentioned earlier, since its mechanical energy needs to be constant, we know that this is pretty much just going to add up to 4, since 4 plus 2 is 6. And that kind of makes sense too, because think about it. If it's over here, right, it's going to be mostly kinetic energy, and at that point, it's still going to be mostly kinetic energy, but it's still going to have some gravitational potential energy because it is above the horizontal. So this answer is reasonable and it makes sense. Okay, so what does the second question ask us to do? It says that we need to derive an expression for the speed of the block at point B. We need to express our answer in terms of r and physical constants as appropriate. So how do we do that? Think about it. Conservation of energy is how we did this problem, and you realize that kinetic energy, it's 1/2 mv squared, and that v represents the velocity. So we can use conservation of energy to get our answer here. So how would we set that up, right? So first let's write down what conservation of energy is, like the basic formula for it. And that is going to be potential initial plus kinetic initial is equal to potential final plus kinetic final. And you know why is that? It's because mechanical energy, which is the addition of potential and kinetic, it has to stay the same. There's no non-conservative forces. So energy is conserved. Now, we did our calculations here at point B, right? We can use this as well. So what is our initial gravitational potential energy? So if you look here, this is the initial point. This is what we're starting with. So we can see that it's going to be mgh h plus no kinetic, because see, it's stationary here, so no kinetic. And what is it equal to? So at point B, what is our gravitational potential energy? So as we said here, right, it's going to be 2r mg, because it's mgh, but it's just going to be 2r because it's at this point and the circumference of this circle is 2r. So it's going to be mg 2r, and then plus some kinetic energy value because it does have a velocity at this point. So plus 1/2 mv squared. Okay, and then this h we can replace with 6r because that's the initial point. Let me do that real quick. 6r. Right? So this makes sense, right? Because it starts with 6r mgh or mg, and then it ends with the potential. It ends with some potential energy and some kinetic energy. So let's solve this out, right? Now it's a pretty simple calculation. We multiply 2 by both sides and take the square root. So we have v equals root 8rg. Now one thing I like to do when we get to a final answer is make sure it seems physical. Make sure intuition, make sure there's some extent of intuition that makes sense, right? So what this is telling us is that point B, right, its velocity is going to be 8rg. So if the value of r was increased, right, that would make sense, because then it's gonna go faster. If you drop it from a higher point, it's gonna go faster at this point, right? So in terms of intuition, it does make sense, and gravity is a part of that. So overall, this seems right. And for an AP exam where you have such limited time, that is really gonna help you. You're kind of using intuition to answer these problems. Okay, now we have this question. Part C. On the following dot, which represents the block, draw and label the forces, and not components, a pretty important part, that are exerted on the block at the instant the block slides through point C. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So this is basically a force diagram that we're going to do here. So let's see, point C they said, right? So at point C, let's see what's happening. The block is, it's gone through this circular loop and it's on this one, and it's at the top part of this circular loop. So it's going to have some velocity, it's going to have a decent bit of gravitational potential energy. So we know that. But what about the forces, right? So think about it. Let's place a block here. What forces would be affecting this block at this point? And now this is kind of like you have to use your logical thinking skills. There's going to be gravity. There's going to be gravity at all of these parts. So we know that there's for sure a force of gravity. But now here's the tricky part. There is another force. And because there's direct contact with the circular loop, there's going to be another force. And that's going to be the force, and that's going to be the normal force, and it's going to point this way with a slightly higher magnitude. Now, why is that? Think about it. It's a circle, right? And in circles, we've studied that there's a centripetal acceleration. So this block is going to accelerate towards the center of the circle. Now, for that to happen, there needs to be a force that's pointing in the centripetal direction. That's not force of gravity, because remember, even in this point, force of gravity is going to point down. It's going to point down all of these points. So what's the centripetal force? It's the normal force that's exerted on the block by the loop, right? Because that's the only centripetal force that actually makes sense in the scenario. So we have our two forces, force of gravity, and you can just label it like that, or you can say mg, and then the normal force. Force normal. And that's it. It's a pretty simple question. These are not components, these are forces that are exerted on the block. So next question, part 2. A student claims that 4r is the minimum height of point A. And we just have to prove that this claim is incorrect from what I'm understanding. So let's see. So 4r is the minimum height that the block can go without losing contact. So when does the block lose contact? And that's when this block right here, it has a velocity of 0. That's when the block's really going to lose contact, right? So let's see, 4r. Just say if this was not 6r, this was 4r, what would the situation be like? Let's see. So we would start, first of all, we can do conservation of energy again. UG plus, or no, sorry, U initial plus kinetic initial is equal to U final plus kinetic final. So let's actually do it, right? So mg 4r in this case, because it's starting at 4r, and then plus 0 because it's still not going to have any initial velocity. Then we're going to have what's going to be the potential energy at this point? Let's see. So we have 2r, and then plus another 2r. I know it's not to scale, but it is how it is. And then, because the circumference here of the circle is going to be 2r, so it's going to be a total of 4r above the horizontal. So let's do that. mg 4r. So, and then plus whatever, 1/2 mv squared. Now, one thing you'll notice here is that mg4r, mg4r, these cancel out. I mean, if you subtract them, you're going to have 0 is equal to 1/2 mv squared. So in that case, v must be 0. So when we're doing this scenario, when we're running numbers, we're getting that velocity at this point, at point C, is going to be 0 if the starting point is at 4r. And you know what that means? When the velocity is 0, obviously this block is going to lose contact, and it's going to eventually just end up falling. So we can say that it can't slide through point C without, it cannot slide through point C without losing contact because its velocity is at 0. And to write that, you can just write since Vf equals 0 if v, I'll just write it with normal text. Let's do that. Yeah. Since velocity final, I'm just gonna write it like that, equals 0 when the initial point is at 4r, right? Based on conservation of energy, the block will lose, I don't know if it's getting on screen, the block will lose contact and will eventually fall. And therefore we prove the student is wrong. And that's the FRQ.